chalk seems
Maybe
to...
I should use this.
She just used it, actually. I
Oh,
think the
it's
chalk
this.
should go fine on it. When Raphael Flaudger was speaking last week, he would... Most speakers using the eraser, but he actually did this after every board, and he would just write on it immediately afterwards, and it was fine.
Oh, okay.
So
Okay.
I think it should be okay.
Freddy telling us about scattering amplitudes.
All right. Well, thank you very much to the organizers for inviting me to this beautiful place, my first time here. And I'm also very happy that we're going to be talking about scattering amplitudes, even though last year TASI was mainly about scattering amplitudes. So when Joao said that the motivation, part of the motivation for discussing conformal field theories was that David gave a lecture, a sequence of lectures last week, I would say that the motivation for studying scattering amplitudes is that a whole TASI lecture or a whole TASI course was dedicated to scattering amplitudes last year. Well, that's the motivation. So the motivation for sitting here through the next 4 lectures is that you were not here last year. Okay, so why study scattering amplitudes? Well, I can give you many reasons. They are the main observables. We measure things at the helicity, scattering experiments. We have to compute cross sections. Well, but you would say, well, we all know how to compute the scattering amplitudes. We learned that in quantum field theory 1 when we learned Feynman diagrams. So almost everything that I'm going to tell you today are things that you actually know how to compute, or in principle, you know how to compute. Okay? But what we're going to see in the course is that in the past 10 years or so, we have learned that even though Feynman diagrams give us the answer to what I'm going to explain, Feynman diagrams are not the most efficient way to think about it. And in fact, they sometimes obscure properties of the scattering amplitudes. In the past 10 years or so, we have discovered many different formulations of scattering amplitudes that make manifest different symmetries and make manifest very surprising connections to mathematics we never expected were going to be related to the most boring objects that you compute in quantum field theory 101. So the basic example for these lectures, well, you can guess what it's going to be. It's exactly the theory that Joao was talking about. It's going to be a UN gauge theory. Which eventually is going to get supersymmetrized, and it's going to become n equals 4 super-Yang Mills. But for the time being, this is just a UN gauge theory, and we're going to consider the scattering amplitudes of gluons. Now, how do we describe gluons? Well, at least in perturbation theory, okay, we pretend that they are asymptotic states. Of course, they aren't, but let's just pretend. And then they are described by momentum vector, a polarization vector, and the notation here is a little funny, but I'm using different different fonts. Okay, so here, using this, I don't know, I think this is Romans. So this index goes from 1 to n squared, and this is going to be the color index. So gluons will come in n squared varieties, and they are related to the n squared generators of UN. So we have polarization vectors, of course. We take the polarization vectors to be transverse, and we're going to start studying the scattering amplitudes of n gluons something that is I hope very familiar to everybody, is that you compute the scattering amplitude starting with a correlation function, say momentum in coordinate space, then your Fourier transform. By general principles, this object should have poles wherever particles go on shell, the external particles go on shell. So you compute the multidimensional residue of that object, and that's how you get the scattering amplitude. Now, a consequence of starting with a correlation function in coordinate space is that the correlation function has to be translation invariant. So translation invariance implies of the correlation function in coordinate space implies that this scattering amplitude is not a function. This object is a distribution. And here, for the time being, I'm going to think that we are working in RD minus 1, 1, or R1, D minus 1, depending on your choice of signature. And it's not a function because it only has support on set of momenta that preserve momentum conservation or that impose momentum conservation. And here we have a sum over Feynman diagrams. Okay. And this is the thing that you know how to do. Okay? Now, in your courses, you probably did the scattering amplitude of scalars. And you probably didn't do the scattering amplitude of gluons, at least for more than 4 particles. And part of the reason is that all this structure, the color structure and the polarization vectors, make the computations incredibly complicated. So people have developed techniques to simplify the problem using the idea of divide and conquer. So we're going to divide the problem by using something that is called the color decomposition. So what's the idea? Well, in Young-Mills, or in gauge theory, we know that gluons interact, or the interaction vertex, say the 3-particle interaction vertex. Of course, it has several structures, but the color structure of the interaction vertex is something of the form is governed by the structure constants of the gauge group, which I'm going to write as well, this looks like a funny way of writing it. Of course, it should be trace of the generator TA1 and the commutator of the generators TA2 and TA3. But you're going to see why I decided to split it up and write it as different traces. Okay? Good. So now, considering a simple example, in order to understand why this is useful, let's consider the following Feynman diagram for the interaction of 4 particles, 4 gluons. So we have 2 interaction vertices. Now, we can sit here and write the whole contribution to the 4-particle amplitude coming from this Feynman diagram, okay, with all the kinematic factors and everything perfectly, but that would take us the whole lecture. So instead of doing that, I'm going to concentrate only on the color part and let you, as an exercise, fill up the rest, okay? So the color part is going to be what? Well, according to Feynman, we are supposed to sum over all the possible particles or all the possible structures that can go from here to here. So if this interaction vertex connects gluons 1 and 2 with an internal gluon B, we are supposed to sum over B from 1 to n squared, and then connect that at this vertex with gluons 3 and 4. So as I said, this is just the color part of the Feynman diagram. So it would be this times kinematics. Okay. Now I use my fancy identity, or my trivial identity over here, right? It's actually trivial, to write each of the structure constants in that form. So I'm going to sum over B. So I write the first one as a trace of TA1, TA2, TB minus trace TA1, TB, TA2, and the second one okay. Okay, warning, reaching levels. Okay, very good. So applying a small conformal transformation to make the, so we have trace of TB, trace of T3, and trace of T4, TA4, minus TB. So that's good. I thought I had made a mistake somewhere, but okay. Now we use another deep identity of UN, which is the following: is a completeness relation which says that if you have a trace with dot 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 TB, and you have a trace of TB and this, the triangles and the dots are important. You sum over B from 1 to n squared, and this becomes a single trace. So in UN, if you sum over the generators, you can actually fuse the traces. So you can call this a fusing identity. So you get trace of dot dot dot. Okay, very good. So now we can use that identity here and see what happens. So we take the first term with this term, and we get trace of TA1, TA2, A3, A4. Now we take the first with this one, we get trace A1, A2, A4, and A3, plus two other terms. Okay? So I hope I've convinced you with this simple exercise that when you have three-level diagrams, any three-level diagram, not only for 4 particles, but for any number of particles, you can play this game over and over again. And every time, you can fuse the traces. And you do it until you get a single trace. Now, that's going to happen for every single Feynman diagram. So a single Feynman diagram, as you have seen here, can contribute to many different traces. Okay? So this particular Feynman diagram contributes to 4 different orderings of labels inside the trace. Now what I'm going to do is to say that I'm going to collect everything, the contribution from all the Feynman diagrams, not according to their topology or according to the kinematics, but according to the trace structure. So I'm going to have a term that comes from collecting everything that contains or contributes to this particular ordering from A1, 2, up to AN. And I'm going to call this, note the change in notation. So this was calligraphic A, and this is a standard A, okay? Maybe Times Roman or something. So you have 1, 2, up to N. So this is called a partial amplitude. And the reason is that this is not the complete amplitude, because now you have to sum over other trace structures. Okay? how many traces structures would there be? So how many terms are there in this sum? n minus 1 factorial, right? You would say that n factorial because you have permutations of n elements, but the traces are cyclic, so you have to divide by n. So you have n minus 1 factorial terms here, okay? But of course, once you compute this one, you can start to gain some mileage because maybe you will have some symmetries that will allow you to compute some of the other ones once you compute a smaller number than n minus 1 factorial, okay? Very good. So that's the definition of this object. So by definition, yes. Very good. So at tree level, we only have single trace and these objects with W a permutation modulo cyclic is called a partial amplitude. So what do you think is going to happen at one loop? Can we have single trace things? Yes, we're going to have single trace objects, but we will also have double trace objects. Okay. Very good. So now you're almost there. You at least have part of the terminology when you hear talks in amplitudes. People will usually talk about these partial amplitudes without telling you. So at least you know what they are doing. Or at least the definition of these objects. But now we have to keep working and do kinematics. Why do we have to worry about kinematics? Well, the reason is that we have k vectors they have to satisfy a linear constraint, but they also have to satisfy n quadratic constraints. Well, writing functions that depend on variables that have to satisfy quadratic constraints will very likely obscure properties of the object. It's very easy to find examples. I'm sure you have come across examples of objects that when you write in certain number of variables, in certain variables, and the variables satisfy a constraint and you don't impose it, the object doesn't look nice. For instance, if you try to solve, well, the standard example is, say, you try to solve the hydrogen atom and you use coordinates where, say, Cartesian coordinates. So things will look ugly, right? Or imagine that you try to solve exactly some classical mechanics problem on a sphere and you use also Cartesian coordinates subject to the constraint that the x squares add up to the radius of the sphere. So the answers will not look nice. So we have to find a way of getting variables where these constraints will be either linearized or they will be automatically satisfied. So it turns out that this is actually possible or is convenient, or there is a nice representation in d equals 3, 4, and 6. In dimensions 3, 4, and 6, there is a very nice way of representing these objects. For the time being, or for today, we're going to concentrate on d equals 4. So in 4 dimensions, this goes by the name of the Spinor helicity formalism. Okay? And the idea is very simple. You just collect the Pauli matrices as a 4-vector, and you contract every vector that you have with your 4-vector of Pauli matrices in order to produce a 2x2 matrix. So this 2x2 matrix has a very, if you haven't seen it before, it looks like a very awkward notation for the components. So let me actually introduce it for the Pauli matrices. It's a 2x2 matrix, and people denote the indices as alpha and alpha dot, or Greek indices and dotted Greek indices. And the idea of introducing two different kinds of indices is because the Pauli matrices actually transform under 3 different representations of the Lorentz group. They have a vector representation, a Spinor representation, and the conjugate Spinor representation. So this is a way of remembering how the object transforms. And now these 2x2 matrices that we have constructed also have the 2 indices. Of course, the vector index has been contracted, so we are going from a vector representation. This is a way to translate from a vector representation to the bi-Spinor representation. So does anybody know what the determinant of this matrix is? Yes, it's 0. But more generally, the determinant of the matrix agrees with the norm of the vector in Minkowski space. So this is actually equal to k a mu, which in this case is 0. And that brings us to the reason why this transformation from vector representation to the bi-Spinor representation is useful. And the reason is that if this matrix has determinant 0, it means that it has a null vector, or it means that we can write the columns and vectors, or the columns have to be proportional to each other. So the constant of proportionality here is A and here is B. Okay? So this is the most general 2x2 matrix that has determinant 0. Okay? Is that clear? The most general 2x2 matrix with 0 determinant can be written in this form. Now, this is not quite the way we're going to follow the notation, because it doesn't make manifest the fact that this object should transform in the bi-Spinor representation. So the way we're going to denote the entries is as follows. We're going to introduce a Spinor for each particle. So here we're dealing with particle A, so there is a Spinor A that has an index alpha, and there is a Spinor, a conjugate Spinor that has an index alpha dot. Now you can see that they are the corresponding AX, BX, AY, and BY. Okay? So now for each particle we have to give, instead of a vector, you're going to give me now a pair of spinors. So here is your first exercise. Well, not the first. I think I gave you some exercises before. But so the first formal exercise is show that if you have two vectors and you contract them, the factor of 2 is important. In other words, this is the same as Ka plus Kb squared. It's the same because these are null vectors, so the individual terms squared are 0. This happens to be equal, or it should be expressible in terms of these objects. And the way it's written is as follows. It's going to look a little awkward, but Well, epsilon and epsilon tilde are antisymmetric matrices, 2 by 2 antisymmetric tensors. And these objects are the basic SL2C invariant objects. And they are going to be the building blocks of our amplitudes, because our amplitudes started their lives as being functions of these kinematic invariants. But now they will be functions of these other kinematic invariants. So we should give them a name. Okay? So we can discuss by both what names we're going to give, but since I'm giving the lecture, I can choose the name. So the name for this is going to be, this is actually an inner product, just as much as this one was. So we can choose a notation for the inner product to be AB. Now this one, we cannot use the same notation. We have to find a way to distinguish it. So as good as any other notation is that square bracket. So don't confuse it with commutators. This is just a notation for this particular inner product. OK. Very good. Now, if we were dealing with the scalar particles, we would be done. This is all that we will have to discuss. But we are not doing scalar particles. We're doing gluons. So gluons in 4 dimensions, actually any massless particle in 4 dimensions, the representations, they are representations of the Poincare algebra or the Poincare group, and they are classified by something called helicity. And gluons come in 2 varieties. They can have plus or minus 1 helicity. Okay? How about gravitons? They will have helicity plus minus 2. So sometimes people call the absolute value of the helicity, they call it the spin. It's not really a good name because there is something else that is called the spin. But given that we have, or we believe that CPT is a symmetry of nature, so every time we have a theory with particles with a given helicity, we must have the particles with the other helicity as well. So it's good to talk about them as a single object, even though from representation theory, you could very well imagine having a theory that only has particles of helicity plus 1 or particles of helicity minus 1. So how can we tell? Well, polarization vectors are the ones that are supposed to tell you. So if you have a polarization vector, polarization vectors will be different depending on the helicity. And now what I'm going to tell you is what happens if the helicity is minus 1 and you contract the polarization vector with the Pauli matrices to make a 2 by 2 matrix. This object is going to be the following. Of course, it has to depend on the particular particle we're dealing with. So this is for particle A. So we have the particle index, and the object has to satisfy the property I mentioned over there, that it has to be transverse, so it has to dot to 0 when you contract it with Ka. Okay? That already gives us a hint. If we want something like this to be 0, we have 2 options. Either we make this equal to 0 or we make this equal to 0. These objects or these inner products are antisymmetric. So if A happens to be equal to B, if lambda A happens to be equal to lambda B, you get 0. Or if you get lambda tilde A to be equal to lambda tilde B, you also get 0. Okay? So we can satisfy the transversality constraint by saying that the lambda part of this object, of course, this object is also defined to be null. So it also has a lambda and a lambda tilde representation, or a bi-Spinor representation of the same form. So we can choose this one to be lambda. And there will be something else here, which I'm going to try my best attempt at drawing at zeta. But I mean, it's just that, yeah, it's not, that's my best. Okay? So this is going to be a reference spinor. Since we cannot choose it right now, I mean, it's just, there is no reason to choose one or another. We chose this because it makes that property manifest. Okay? And there will be some normalization. Sorry. And the normalization is chosen so that it doesn't depend on the scaling of the reference spinor. Okay? So the natural choice is an SL to C invariant. And the only other choice that I have that has the data of the 8th particle is a lambda tilde of the 8th particle. Okay? But I could also have done the same thing, reversing the orders of lambda tilde and lambda. And luckily, there is only one more polarization vector that I have to define, which is a one for particles of helicity +1. And that one is going to be something of this form. Okay? So I already showed to you that this was true. And now here is an exercise. Is the following. Show that a change in the reference spinor is equivalent to changing the polarization vector by a quantity proportional. Let me put here the index A. I put the index mu up. Proportional to the momentum vector of that particle. Okay? So that's actually great, right? Because we know that this is a redundancy we have to mod out by. In other words, the amplitudes must be invariant under this replacement. But if the choice of reference spinors, is equivalent to this, then this is a valid representation of our polarization vectors. Okay. Now, something that nobody asked, but you could have, is that the number of degrees of freedom they don't quite match here. A null vector in 4 dimensions has 3 degrees of freedom. And these objects, this one has 2 degrees of freedom and 2 degrees of freedom. So we have 4. Okay? That means that in order to define a momentum vector, we can use equivalence class of spinors. Okay? And the equivalence class is the following. If you have 2 spinors, somebody gives you these 2 spinors, you say, no, I don't like them for whatever reason. I want to choose to rescale the first one that you gave me by a non-zero quantity, non-zero complex number Ta. But then you have to rescale the other one by the inverse of that one. And this equivalence relation tells you that the momentum vector that you construct is invariant. Are the polarization vectors invariant under this transformation? No, they are not invariant. So this transformation actually corresponds to a little group transformation. Okay, so under a little group transformation of that form, I'll let you see what happens to the polarization vectors. So you should figure it out. While they scale. And we don't have the mu's now because these are 2 by 2 matrices. Okay? So I want you to figure this out in the time it takes me to erase some of the blackbirds. Okay. So and this lecture goes until 12, right? Okay. Okay. So much for kinematics and definitions. So let's actually try to determine some amplitudes. So let's start with the simplest possible one, which is an amplitude of 3 particles. And we're going to assume that the first particle has helicity -1. So now the helicity is going to be denoted. This is going to be the notation. So I'm going to have the particle index and the helicity. This is a shorthand notation for a lot of things. For the spinor, the conjugate spinor, and the helicity. Okay, so every time you see something like this, what it really means is this. Okay. So now it's clear that if I give you the helicity and the pair of spinors, I don't have to give you anymore what the polarization vectors are. You already know what they are. Okay. So all the data that you need to compute an amplitude is this. I don't even have to give you the color index of the gluon. And the reason is that we're only computing partial amplitudes. We're not computing the full calligraphic A. Okay? So this is the coefficient of trace of A1, A2 times A3 in an amplitude where gluon 1 carries negative helicity, gluon 2 negative helicity, and gluon 3 positive helicity. And what is the answer? Well, the answer is some coupling constant. And I'll tell you what the answer is. Okay. Now, is this surprising? Is it surprising that the 3-particle amplitude only depends on these brackets and not the other brackets that I mentioned? Well, it might be a little surprising, but note the following. Note that if you have 3 vectors that satisfy momentum conservation, this implies is that Ka.Kb is equal to 0 for all A and B. Well, the way you prove this is that you move 3 to the other side and you take the square. The vector is null, so K1.K2 is 0. Now you move 2 to the other side and you leave 1 and 3 on this side. You square and you get 1 and 3 equal to 0. So isn't that surprising? You get that all the kinematics invariants are 0. And that's why you learned in quantum field theory that massless particles cannot possibly decay, or they cannot possibly scatter to produce 2 to produce just a single one. Okay? Now, why did I write something that was non-zero here? Well, the reason is that this is actually 0. Well, I'll show you why it's 0. The reason it's 0 is that this, as we show over there, is AB times AB. So you would say, well, only one of the two have to be 0. But if you are dealing with real kinematics, the conjugate spinors are the conjugate of these spinors. So if this is 0, this is also 0. So for real kinematics, both of them have to be 0. And here you have 3 zeros in the numerator and 2 zeros in the denominator. So this is 0. Okay? But that's such a pity. This object looks so beautiful. It has so much structure. It even knows about the helicity, right? Check the helicities. So if you rescale particle 1 according to the rule that I gave you there, you're supposed to get an object that transforms as follows. If you did particle 1 by T1 and T1 inverse and the 1 tilde, this is supposed to go to T to the minus 2, 1, A, lambda 1 tilde. And I hope this one does it. Does it do it or not? No, it doesn't do it. And the reason it doesn't do it is that I'm probably using the wrong formula. So did you check what happens here? What is it? Minus 2 times the helicity. So I'm glad somebody did the exercise while I was erasing. So this one has helicity minus 1. If I use that formula, it should be plus 2. Does it work now? Yes, it does. So it's such a pity that this formula that knows so much, if you do it for 3, it also works. It's supposed to go to T3 to the minus 2. And you have 2 in the denominator, so it works perfectly. That such a formula has to go to waste. Well, remember that the 0 came here because we insisted that one of them was a complex conjugate of the other one. So lambda has to be related to lambda tilde if K is Hermitian, which if and only if K is real. But who cares about real spacetime, really, right? So we can make K complex. So make K complex, which means that K, the matrix K, is not Hermitian. And lambda is independent of lambda tilde. Okay? Now you would say that's all right. So that means that we have 2 choices. When we have 3 particles, we can always choose either all the lambda tilde brackets to vanish or all the lambda brackets to vanish. One of the 2. Now we are like in conformal field theory. Somehow Lorentz Poincare invariance and translational invariance here imply that the function can only be a function of one of the brackets or the other ones. These transformations, which are like the scaling dimensions, are fixing completely the 3-particle amplitude. But you would say, wait, why didn't you write this? You could also have written this object. This one also scales correctly. It has the correct little group properties. But what's wrong with this object? Can anyone tell me? Why do you think we have to throw that away? Well, we are crazy, but not that crazy. If we complexify momenta, both things are completely fine. But we also want to go back to the correct answer once we go to the real slice of complex momentum space. So once we go to the real slice, every bracket that you see goes to 0. And as I said, this one has a 0 cube and 2 zeros in the denominator. So it goes to 0 as it should. And this one blows up. So this solution is unphysical. So we have to throw it away. Okay. Okay, so we did it. We computed one amplitude. Too bad there is 0 in real momentum space, so we better get something more interesting than that. Okay. And it turns out that, let me check the dates. Right. So let me write the dates. So Parke and Taylor decided to take the challenge and use this Spinor helicity formalism to compute things that were useful for the Tevatron. I mean, this is 85 after all, right? So in 1985, they decided to calculate the 4, the 5, and the 6 particle amplitudes in the following helicity configurations. So they chose, let me write the 6 particle amplitude. Well, I'm being lazy now. You see, every time I'm removing more structure. From here to here, I removed the lambdas and the lambda tildes, and this was left. And now I'm going to remove even the 1, 2, and 3, and just write the signs, okay? So what do I mean by this? I mean the partial amplitude where particle 1 has negative helicity, and so on, okay? So they computed this one, and they got 0. They computed this one, and they got 0. Then they went on and said, okay, so let's change 1, and they also got 0. And they changed 1 here, say this one. Of course, they also got 0. And they get 0 because a parity transformation sends this one to this one. Okay, so if this one was 0, that one also had to be 0. So that was not surprising. This one was more surprising. Okay. Now you see that, and then you say, maybe if I put another plus, I'll also get 0 after all. But it turns out that the next case, where you have some minuses and 1 and 2 pluses, is not 0. Okay. So here, the same thing. You have all pluses, and only 2 particles are minuses, and these ones are non-zero. Okay? In the interest of time, I'm going to jump from 6 to m particles. Okay? So they calculated these amplitudes in 85, and they found that this paper has, I think, 14 pages, and only 3 pages are of text. What do you think the remaining pages are? Yes? The answer. So, and that answer ends up collapsing dramatically once you use these Spinor helicity variables. And after seeing that miraculous compactification of the answer, they decided in 86, they made a conjecture for what this amplitude is in general. Okay? So without any hope of actually checking it, because already the 6 particle amplitude was too complicated to, I mean, it's incredibly complicated in their calculations. So the answer ends up being equal to, so if this is particle I, and this is particle J, and the rest are pluses, the answer ended up being this. As simple as this. That's completely spectacular. I mean, out of hundreds of pages of calculations, you end up collapsing everything to something that looks like this. And they saw that it was working for 4, 5, and 6 particles. I think they even did 7. And they conjectured that it was true for any number of particles. Of course, I'm missing some coupling constant, but I'll let you figure out what the power of the coupling constant is. Why is there 1, 2, 2, 3, and so on, and not a 1, 3? Would you be able to tell why? Well, if there was a 1, 3, you can then multiply by 1, 3. And what is this object? Maybe we still have it. Yes. The product of these two brackets becomes this, right? So this would give some structure in the numerator that looks like this, which could easily come from the contractions of the polarization vectors, no problem. So that's not the problem we have. The problem is that there will be a pole of the form K1 plus K3 squared. And that would mean that there was a propagator in a Feynman diagram that had that structure. But this is actually impossible for diagrams that have or that multiply the trace of TA1, TA2, up to TAN. These are diagrams that can be drawn on a plane. If you draw a circle and put the order 1, 2, up to n, the Feynman diagram has to be drawn, you have to be able to find a planar embedding so that the Feynman diagram is drawn on the plane in order to be able to produce such a trace. But you can convince yourself that no Feynman diagram that has that property can possibly have a propagator of the form K1 plus K3. Okay? So in that way, you can guess that the answer can only have a certain kind of propagators. But now you would say, why not propagators of the form K1 plus K2 plus K3? Those would be valid, square. Well, for that, you'll have to wait a little bit. But knowing a little bit of what the amplitude has to satisfy, you can see why this makes sense, at least the denominator structure. Once you figure out the denominator structure, the numerator comes from the helicity. Okay. Okay. So of course, a subject doesn't evolve if you don't have visionaries, right? So sometimes all it takes is one person plus 10 years, but sometimes all it takes is one person and then another one who rediscovers what the person did. But here the visionary so is Nair, who came around and looked at the formula. And he said, well, this formula actually looks right. Not only looks right, it looks so beautiful that it must have another meaning. So in the year, so Nair did it in the year 88. In 88, only 2 years after that, after the conjecture was made, Nair said, well, this formula is begging for a new interpretation. Okay. So what did he know that people didn't usually know? People who were doing these calculations didn't know. Well, he knew two things. One, here is advertisement for CFT, so keep working hard on CFT. That's very useful. But he also knew twistor space as developed by Penrose in '67. So he knew these two things, and he realized that these lambdas, he knew that these lambdas, let me write them like this, are, or can be thought of, yes? Yes, okay. Are homogeneous coordinates on a CP1. Okay? Or at least that's what they look like. Okay? And if that's the case, he also knew that if you have fermions on a sphere, their correlation function goes like the difference of the positions on the sphere. So he said, this looks like some sort of correlation function on a sphere. Then the question was, which sphere? And which correlation functions? What theory is computing this object? Okay. So in order to do that, let's discuss a little bit about twistor space. Okay. So what's the idea? Imagine your Penrose, and that's hard to imagine. I mean, it's even hard. But just for a second, let's imagine your Penrose, and you come out with this idea that you become obsessed with two things. He also became obsessed with two things. He became obsessed with complex numbers and CFT and conformal transformations. So the way he became obsessed with conformal transformations was becoming obsessed with null rays or null particles. He was way ahead of his time. In the 60s, when people were obsessed with massive particles, because that's all there was, okay, you were discovering hadrons all the time. Every day there were new hadrons. They were all massive. And the only massless thing that we knew at the time was a photon. So the photon was considered kind of an exception. So it was a kind of a strange thing in nature. Instead, Penrose thought that what you had to do was actually to think about null rays in space-time as the fundamental objects. The trajectories followed by null particles were fundamental objects in space-time. Okay? So you have null rays. So he thought that you need a space of null rays. So how do you describe a null ray? Well, to describe a null ray, you choose a particular time, okay, maybe now, okay, or now would be equally okay. So you choose one particular time, and you choose a point where the null ray passes through, okay? So that would be 3 coordinates. And then you have to give me where the null ray is going to end or the null ray came from. So where it came from is like when you look at the sky at night, you see the celestial sphere. So you see a sphere. So there is a sphere. And the null ray came from a particular direction. So you have to give me 2 coordinates on the celestial sphere. Now what got Penrose excited was that this celestial sphere is not any kind of a sphere. It's a complex manifold. So Lorentz transformations actually change things on the sphere in such a way that they preserve the complex structure. So this was no ordinary sphere. This was a CP1. Okay? Very good. So he wanted to find a way to create the space of null rays. A space of null rays is a space where each point corresponds to a particular null ray. So let me denote the null ray like this. And here it is. Okay? Very good. So what do you do with that? Well, you say, well, what could this space be? Well, this space is clearly something that is 5-dimensional. Penrose wasn't happy about that because you cannot make a complex manifold out of a 5-dimensional space. But he had something to do later to fix that little problem. But then what he decided to do is that, well, a particular direction on the sphere can be described also by a coordinate, lambda, on the CP1. And he introduced what is called the incidence relation, which is the family of points belonging to the null ray. I'm going to call them by x. And the particular direction on the sphere is going to be lambda. And this is going to define a new object, mu. Now, this point is going to be denoted by lambda and mu. This is a 4-dimensional object, which he calls z. Okay? But of course, any choice of z and another choice of z obtained from this one by multiplying by a non-zero complex number would be completely equivalent, because this incidence relation is invariant under that transformation. So you have to define this equivalence relation where T belongs to C star. Okay? And that's how this space was born. So it's a space of 4-dimensional objects, 4 complex dimensional objects, mod by this relation, but that mathematicians have a name for it. So that space is called CP3. Okay? And the way to think about it is as points in C4 modulo this relation. But I told you that this was a 5 real dimensional space, the space of null lines here. And the reason is that if you choose any random point here, again, your matrix X will not be Hermitian. It will not correspond to a particular point in space-time. So you have to impose a reality condition on these objects. And the reality condition is a condition that tells you that Z dot some particular definition of conjugate is 0. But this is only a 1 real dimensional equation in a 6-dimensional space, because 3 complex dimensions are 6 real dimensions. 1 real equation brings you down to 5 dimensions. So the twistor space of real space-time was a 5-dimensional object sitting inside CP3. Okay? Very good. But once again, who cares about real space-time? You can complexify everything, and now you can live happily in the full CP3. All right. So yes, Nair knew all this. So he conjectured that these amplitudes with only 2 minuses and the rest pluses are correlation functions on a CP1 living in twistor space. Okay? Now, again, you could have asked, but you didn't, what happens to the other amplitudes? What happens if you keep going? Put another minus. Would the answer be as simple as this? Well, of course, people tried. After seeing how beautiful this was, you put another minus, and now life gets complicated again. So everything is messy, nothing nice happens. Okay? So, and the complication gets worse and worse the more minuses you add. Of course, at some point, everything reverses again, because when the number of minuses wins the number of pluses, things start to get easier and easier until you get back to this case, which, by the way, is just given by the complex conjugate, or by the conjugate version of this, where you exchange these brackets by these brackets. So physicists started to develop a way of calling these amplitudes by the complexity, how complex they were or how difficult they were to calculate. So the simplest kind, yes? Well, that's the point. When you're a visionary, things don't come from anywhere. And in fact, we're going to find that the conjecture is not exactly right. I mean, it was fairly close, but let's continue for a little bit, and then you're going to see what happens. Oh, yes. Okay. Right. Okay, very good. Thanks. So what Pedro is saying is that if you have homogeneous coordinate on the CP1, you can go to some inhomogeneous patch, or you can actually rewrite this as follows. You can say that this can be reparameterized in this form, okay? And then you can show that the determinant, or this angular bracket of AB, becomes nothing but TA times TB ZA minus ZB. Okay? Okay, good. Very good. Now, I'm not sure I have time to explain why, but these amplitudes that Parke-Taylor found, the amplitudes where you have the number of negative helicity gluons is 2. These are called maximally helicity violating amplitudes, okay? Or MHV for short. Well, I have to say, right? I mean, how can I just tell you that this is the name and not tell you why they are called like this? Well, the reason is that, as usual in quantum field theory, I'm assuming that all these particles are incoming or all these particles are outgoing, right? But in physical processes, some particles are incoming and some particles are outgoing. And you can check that if you started with the amplitudes that are 0 at the top, these would be amplitudes where, say, you have particles 1 and 2 incoming, right? But I was assuming that all the particles were outgoing. So I have to use crossing symmetry to change particles 1 and 2 from here and make them incoming, right? So when I use crossing symmetry, I have to reverse the quantum numbers. So I have to apply a transformation that changes this into positive helicity. So I'll now have 2 particles of positive helicity coming in and producing lots of particles of negative helicity coming out. Well, that's what I would call a maximally helicity violating object, right? You have only pluses coming in and only minuses come out. But guess what? It's 0. So that's not the one that violates helicity maximally. This one, which we have 1 positive and 1 negative coming in and then all the rest negative, also vanishes. And the first time you get something that is non-zero is when you go to the next level, and these ones are the new maximally helicity violating amplitudes. So the top ones were the ones that had the right to be called like this, but they actually end up happening to be 0. Now, I have to say that this is true at 3 level. If you take QCD, non-supersymmetric, good old Young-Mills theory, at 1 loop, those amplitudes will not be 0. So they would reclaim the name of maximally helicity violating, okay? But here, for the time being, we're only doing 3 level. So if you have 3 negative helicity gluons, how would you call it? Well, the N stands for next to. Lack of imagination. So you just call it next to MHV amplitudes and so on. N squared MHV amplitudes. So this number here is traditionally called K in some circles. Pedro might call it, I don't think that's a K you're going to introduce. It's going to be shifted by something, perhaps. If he does, I don't know. But for the time being, that's going to be my definition of K. So Nair conjectured that this was true for K equals 2, that you had a CP1 inside twistor space. And then perhaps all others would also work in the same way. And he even came out with the idea that maybe you needed several CP1s connected in some funny way. But he couldn't realize it. Okay? All right. So in the last 6 minutes, I'll tell you about the resolution of this puzzle, how to generalize Nair's conjecture. Let's see. I have a blackboard here. Yes. Okay. And that had to wait, as I said. Sometimes developments take a visionary and many years. So the next breakthrough came in 2003, when Witten decided to look at this and say, well, it's certainly true. That looks pretty much like a sphere in CP3, inside CP3. And CP3 looks like twistor space. So let's actually try to make it precise. So if you take the amplitude, now I'm going to take the full amplitude. Well, it's not going to be the full amplitude. It's going to be the amplitude that we have over there. The same amplitude that Nair considered, but now dressed with momentum conservation. Okay? And he said, well, if you want to connect to twistor space, you might want to bring space-time somewhere and then see what happens. So he rewrote this as follows. Now, Witten also knew about the Spinor helicity formalism, so he decided to write this in a Spinor helicity form. So you have x alpha alpha dot in a Spinor notation, and the momentum vectors are also written in terms of Spinor helicity form. Okay. Now, if you look at what these objects are supposed to be doing, they are supposed to be, or they are supposed to live on things that look like this. How can you possibly get something like that out of an object that looks like this? Well, here comes, I can give you several motivations for that, but I'll just tell you the answer. So he decided to study what is called the half Fourier transform. He said, well, the incidence relation has a lambda, but it doesn't have a lambda tilde. So why don't we get rid of lambda tilde? How can we do it? Well, let's change lambda tilde by its Fourier transform conjugate, or by its conjugate variable. And that object is going to be our mu. Let's see how it happens. So we're going to take that object and define its Fourier transform with respect to lambda tilde. So we're going to do the Fourier transform of every single lambda tilde. So I'm going to write that function, the function that we have over there, say ij to the fourth, 1, 2, up to n1. Here, it doesn't matter that I'm writing too small because this is the object that is written over there that you know very well by now. And we have this integral d for x, e to the I, x alpha alpha dot, lambda a tilde, alpha alpha dot. And we have, now I'm going to put the sum here, from 1 to n. Okay? Now, in this formula, I want the exponential with, oh yes, thank you so much. Yes, this is supposed to be the Fourier transform, so I'm supposed to introduce the conjugate variable. So here there is mu a alpha dot, lambda alpha dot a tilde. Now, the integral, each integral over lambda tilde is an integral of the form each integral is of that form. So it produces a delta function. So I can bring the integral over points in space-time outside and have my amplitude here And each of those integrals we produce a delta function that gives rise to this formula. So this is how the amplitude actually looks like in twistor space, and it shows that the new dependence, each amplitude, depends now on n twistors. These are called twistors. That's why it's called twistor space. So it's a space of twistors. So each amplitude depends on n twistors, and the n twistors are constrained to satisfy this relation. So the n twistors are supposed to be all of them localized. Well, I didn't tell you that. I'll tell you tomorrow. But they are all supposed to be localized on the sphere corresponding to this point in space-time, but not any sphere. Well, actually, Witten realized that it was any sphere. It was actually all possible spheres, because he had to integrate over all points in space-time. So this is a formula that will allow us to go and generalize Nair's idea from k equals 2 to any k. Okay? So I'll stop with this formula today. And this is the key that will allow us to generalize the construction for any k. So this, again, this is for MHP, or k equals 2. Okay? And tomorrow we will generalize to any k. Okay, thank you. Yes?
What's special about dimensions 3, 4, and 6 with respect to spin helicity?
Well, things get actually more and more special the lower you go in dimension. So in dimension 6, you find that the structure of the Lorentz of the little group, which is SU2 cross SU2, allows you to still use something that looks like lambdas and lambda tildes in the construction of the general momentum. Okay. When you go down to 4 dimensions, this is what you get, what I showed you today. And in 3 dimensions, all you have to do is to impose that lambdas and lambda tildes actually are the same. Okay. Now, constructions in higher dimensions are also possible, but the spinors that you have to introduce for these, they have to satisfy nonlinear constraints again. So if they have to satisfy nonlinear constraints, you might as well work with the momentum vectors, because they also satisfy only quadratic constraints. Okay? Yes?
5 dimensions can't be analogous.
Yes, that's right. Yeah, but there is nothing special about 5 dimensions. It just is the standard dimensional reduction from 6 to 5. But there is nothing new. No new structure appears, or nothing special happens when you go from 6 to 5. So you better start with 6.